first theorem. Theorem 10.3 states that if you have the same circle, so in the same circle, or in congruent circles, two minor, so that means arcs that are less than 180 degrees, arcs are congruent if and only if their corresponding chords are congruent. Okay, so if you quickly make this diagram in the picture part of your notes.
I can't see it because people sides.
Well, do you want to move over here so you can see? It might be a better idea. I put the circle there for you so you don't have to worry about making fancy circles. So, let's quickly identify our two chords. So here I have chord AB. Here I have chord BC. Those little tally marks mean what? That they are congruent. So if these two chords are congruent, that means that the arcs created by those endpoints, so, oops, that's really thick. So endpoint A and endpoint B makes arc AB, right? Does everybody see that? Is that a minor arc?
Yeah.
Yeah.
And the others are equal.
And the other one would be arc BC. Let me do this in a different color. BC. Is that a minor arc? Yes. So since the chords created with those endpoints are congruent, what this theorem says is then that the arcs would then also be congruent. Does that make sense?
So you basically need two triangles that are the same.
Right. So the theme of today is going to be equal things together, pretty much, is what we're going to be going through for this whole entire section. Because everything's going to end up being congruent.
Equal triangles, equal angles.
Right. So in circle R, we're given that AB is congruent to CD, which are my two chords. The measure of arc AB is 108 degrees. So what does the measure of arc CD need to be?
108.
Perfect. So the measure of arc CD is equal to 108 degrees. It's not making it any harder than it is. I want all 100% on this quiz on Friday. Okay, questions with that?
Except those like obvious questions that you were talking about it.
Right, that's true. Those the R plus 32 squareds, those are going to be your most challenging ones. All right, theorem 10.4 tells us if one chord is a perpendicular bisector, so think about that. Perpendicular means intersecting at a 90-degree angle. Bisector means it splits it in half of another chord, then the first chord would then be a diameter, which is kind of cool. So here you have chord TR. Here you have chord SQ. If SQ is a perpendicular bisector of this chord, then that means SQ would have to be the diameter.
Wait, what?
So we got our circle. We've got two chords. You got chord SQ. You've got chord TR. If SQ is a perpendicular, so it means right angle, bisector, splitting it in half, then, if you want to write off to the side, then SQ is, well, it's not the, a diameter. Okay, so you might be asked questions like, is this a diameter? And the way you would determine that is if you have the perpendicular part and the congruent, the bisector part. Yes?
What if the bisector was at a different angle, like if it was going in a different way?
What do you mean?
Like, if the bisector wasn't going in at that exact angle...
Like this? Like that? Is that what you're talking about?
Well, see, you move the diameter with it.
So, if I made it like down here?
No, I mean like, if the bisector wasn't at the same like way of going into it.
So if it wasn't a right angle?
Yeah.
So if it wasn't a right angle, and these had to be congruent, then that would force this chord to not be, oh god, I keep erasing things. So if this is bisected by something, then that would force this to not be a right angle. Well, it still looks like a right angle, but then it wouldn't be a diameter anymore.
Oh,
So it needs to have that right angle. Okay?
I get it.
All right. Next theorem, 10.5, is just really the converse of it. If a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord. So in our circle, if I'm given diameter EG, and I know it's the diameter because it's passing through the center point. So if I'm given that it's the diameter, and I'm given that it's perpendicular to another chord, then it's true that FH would be congruent to DH. Okay? So we can check to see if something is a diameter. If it is a diameter, we would have a perpendicular bisector. If you're given a diameter and the perpendicular part, then we can assume the bisection of that part, which means we're going to have congruent parts. What do you do with congruent parts? You equal them together, right? Moral of the story. Good? All right, so let's look at this example. It is asking us to find the length of BD. Is AG a diameter?
Yes.
Why do I know it's a diameter?
It goes through the center.
Goes through the center point. Is that diameter perpendicular to a chord? Yes. So since it's perpendicular to the chord, we can assume that it bisects it. So what's the length of FB? F to B would be how long? 10. So what's the length of B to D? Good. So BD would be equal to 20. Simple as that.
You got the line on top.
Well, remember to talk about lengths, you don't put the line over top. Remember, this means the length of BD is equal to 20.
But isn't the length of BD equal to 20?
Yeah. So we don't put a symbol over top. If I put a symbol over top, then I'm naming the line segment. I don't want to name the line segment. I want to say that it's the measure of BD. All right, let's find the indicated lengths here. So, looking at our diagram, is BD a diameter?
Yes.
Yes, I know it because it goes through the center. Is it perpendicular? Yes, so it's perpendicular. So that means that chord CE is bisected. Well, if I've got bisected chords, what do I know about the arcs, the minor arcs created? If I got congruent,
They're equal.
right? So what are you gonna think? What do you think I'm gonna do to solve for x?
9x equals 80 minus x.
Let's do it. 9x equals 80 minus x. Adding x to both sides gets us 10x equals 80. So what does x equal? 8. Very good. But now I have to actually get the degrees, so we got to plug them back in. What is 9 times 8? That's 72, right? So that means that is 72 degrees. 80 minus 8 is 72 degrees, which makes sense because we said they would be congruent. All right, so what's the measure of arc CD?
And now we can do 360 minus 72 two times and then divide that by 2.
Sure. So we said CD is 72 degrees. What would be DE? 72 degrees. C to E would be how many degrees? Yeah, 72 plus 72, right? So 72 plus 72, which is 144 degrees. Isn't that lovely? Moral of the story, set things equal to each other.
Oh.
C to E, so go the shortest distance from C to E.
So we did nothing with the rest of that circle.
Correct.
I was betting it to do something.
If you were asked to find, let's say, CBD, then it would be everything but what?
72.
Right, so
Or,
we could
or
do-
CBE.
Or if we did CBE, then you would do 360 minus 144, right? All right, last theorem, theorem 10.6. In the same circle or incongruent circles, two chords are congruent if and only if they are equidistant, there's that fancy word again, from the center.
Why not just say same distance?
Or equal distance, because that's
Yeah.
what it means.
So why not just say that instead of this weird word?
It's a few letters shorter than equal distance. Equidistant from the center.
But it's easier to spell as well as say.
So in our circle, I've got two chords. I've got chord AB and I've got chord CD. In order for AB to be congruent to CD, the distance, and think about how do we do distance, the shortest distance is the perpendicular line from the center point. So as long as FE and EG are the same, so if EG is equal to, or EF is equal to EG, then I can say that my chords are congruent. So line segment AB is congruent to line segment CD if and only if EF equals EG. That's what this theorem is telling us. Okay. Again, moral of the story, if we have congruent parts, we're going to set things equal to each
Okay,
other.
This is a weird one. I'm not even sure how to draw this.
What do you mean?
Like this specific way, we have to draw this one.
So if this is the same as that, and it's perpendicular, it has to be perpendicular for it to be the shortest distance, then we're going to have congruent chords.
Okay.
Okay?
I did not draw that right.
That's all right. Why don't you just skip down to the next problem? It's easier done than written. All right, let's find CU. Do I have congruent chords? Yes. So since I have congruent chords, then the distance from those chords to the center should also then be congruent. So what do you think we're going to do to solve for x? Set them equal to each other. So 2x, oh, that's really small.
This is a really complicated looking one.
2x is equal to 5x minus 9. Subtract 5x from both sides. So now we get negative 3x equals negative 9. X is equal to 3. What's it asking us to find? CU. So let's plug it in. 5 times 3 is 15.
It's C.
Oh, CU. Well, it would be the same thing anyways, right? CU's up here.
The other way.
It is. 2 times 3, which is
6.
6. Good. So CU is equal to 6. All right, let's go back and practice some of these before we get to the review.